Let's look at a type of optimization problem where you are trying to find the point on a graph that is as close as possible to a point that is not on the graph. So you could call this a minimization problem because we are trying to minimize the distance from this point to a point on the graph, which if you can draw the graph, which you should be able to draw the graph of square root of x, you can kind of eyeball this and know that it's somewhere in that vicinity, maybe somewhere around x equals 3, x equals 2, something like that. And what we are trying to do is minimize that distance. And so because we are minimizing the distance between 2 points, we will be using the distance formula. And if you have forgotten the distance formula, first, it is just the Pythagorean theorem in disguise. But if you're a fan of just memorizing formulas, it is your change in x is squared plus your change in y is squared. And so in order to measure that distance, we need 2 ordered pairs. Well, one is obviously 4, 0. This other one, which I don't know, I could just call it x, y and use those variables in the distance formula. But since I know that every point on this curve satisfies the equation y equals the square root of x, I am instead going to write that as x square root of x. And now I will apply the distance formula between those 2 points. So I will have the distance is the square root of x minus 4 squared plus the square root of x minus 0 squared. And cleaning that up, we would end up with the distance is the square root of, let's see, x minus 4 squared expands to x squared minus 8x plus 16 plus the square root of x squared is just x. And so finally, I have a cleaned up distance formula of x squared minus 7x plus 16. And so that equation will measure the distance between any point on this graph to the point 4, 0. And I now want to minimize that. I want the minimum of this. I want to find the minimum. What makes that as small as possible? And anytime you see the word minimum or maximum, you should immediately think critical numbers. So I want to differentiate this and set equal to 0, but to make the problem a little bit easier, I'm going to adjust what I'm minimizing. If I want to minimize a square root, if I want to minimize the square root, what I could do is actually minimize what's under the square root. I can kind of ignore the square root, and if I minimize the radicand, if I minimize what's underneath it, I will by default minimize the distance. So I'm going to pull out what's under the radical, and I'm going to call it r for radicand. And I'm actually going to minimize that, and the differentiation just got significantly easier. So I'm going to find the critical numbers. R prime is going to be 2x minus 7. We will set that equal to 0, and I have a critical number of 7/2. Now, graphically, that makes sense. I was guessing earlier my point would be around x equals 3. That is 3.5. So I like that answer. I like that answer. It looks good. Now, I do need to confirm that that actually is a minimum because critical numbers could be a max. And to confirm that's a minimum, I'm actually going to go second derivative test. And so I'm going to find r double prime, which is actually just going to be 2. And so that means that r double prime of my critical number will also be 2, and that is a positive number. If your second derivative is positive, that means you're concave up. If you're concave up at a critical number, then you must be looking at the minimum. So therefore, x equals 7/2 is the minimum of that function of r. And so there I have 7/2, I have the minimum. But the question didn't say just find the x. Let me scroll up. It says find the point on the graph of y equals the square root of x. X equals 7/2 is not a point. That is just an x coordinate. So therefore, my point is is the ordered pair 7/2, square root of 7/2. And I am actually happy just leaving it like that. And there is an optimization problem where you are minimizing the distance from a point not on a graph to the graph itself.